My dear students, I am Dr. Neeraj Upadhyay going to deliver you the module on isomerism in coordination compounds. I introduced coordination compounds in the last class where we learnt about definition of coordination compounds, terms involved in its study and the IUPAC system of nomenclature of coordination compounds. Also, to understand the coordination compound in a better way, I summarized Werner's theory and effective atomic number rule for coordination compounds. When we write a molecular formula for a coordination compound, there may have several possibilities of arrangements of participating group or atoms that can generate different molecular structures. It is needed to understand here that physical and chemical properties of molecule vary with their structures. In short, chemistry of molecules of different structures is different. Werner has used structures of different isomers against a particular molecular formula for establishing his theory. I expect you must read it in your previous classes. If you are not remembered those, relearn from your intermediate textbooks. The learning objective of this class are to identify structural and stereoisomers of the coordination compounds and to establish effect of structures on properties of coordination compounds. Basic knowledge of chemical bonding, qualitative analysis of anions and basics of stereochemistries are prerequisites for learning this class. It is also better to revise the experimental verification of Werner's theory of coordination compounds. What is isomerism? Two or more compounds having similar molecular formula but of different structures are called isomers, and this phenomenon is called isomerism. Since molecules having different structural formula have different physical and chemical properties, it is therefore important to explore all the possibilities and availabilities of such compounds. Because each and every synthesis of the molecule associates with certain target to achieve, and if we know the possibilities of isomers during synthesis of the compounds, we can use certain precautions to get pure desired compounds. Also, isomers can be used to achieve different targets. So, let's focus on the coordination compounds and see what the possibilities of different structures are. Isomers of the coordination compounds can be divided into two broad parts: structural isomers and stereoisomers. Structural isomers can be further subdivided into 5 parts, that are hydrate isomers, ionization isomers, linkage isomers, coordination isomers and coordination position isomers. Similarly, stereoisomers can be divided into parts: geometrical and optical isomers. Let's start our learning from structural isomers. Compounds having similar molecular formula but different arrangements of atoms or groups of atoms are called structural isomers. The physical and chemical properties of such isomers are different. As far as coordination compounds are concerned, structural isomers can be further divided into 5 parts. Hydrogen isomers. In the cases of most of the transition metals, water occupies its secondary valency if no other ligand is available. You all know about copper sulfate. In its most stable state, it forms CuSO4.5H2O and is blue in color. Ferric chloride exists as FeCl3.6H2O. So, for most of the minerals in nature, water acts as a natural ligand. Water molecule may also be a crystallizing agent for some compounds. Such water molecules are called water of crystallization. Depending on role of water, physical and chemical properties of the molecule vary. Coordination compounds having same molecular formula but having different arrangements of water molecules are called hydrate isomers. For example, we know 3 different molecules with the formula CrCl3.6H2O. If all the 6 water molecules act as ligand and occupy secondary valency of chromium, then the framed structure is CrH2O whole 6 Cl3, that is hexaquachromium third chloride. This molecule is violet in color. If one chloroligand replaces a water molecule and water exists as water of crystallization, then the arrangement will be like CrClH2O whole 5 Cl2 dot H2O. The known molecule of the structure is of grey-green colored compound. Similarly, if 2Cl minus ligand act as ligand and 2 water molecules are here water of crystallization, then the formed structure is CrCl2 H2O whole 4 Cl 2H2O. The known molecule of this structure is bright green in color. Like color, other properties of molecules are also different. So you can understand here that the physical and chemical properties by these molecules are different, and those molecules are called structural isomers, and in the specific class that is called hydration isomers. Let's talk about ionization isomers. Coordination compounds having similar molecular formula but different ionization product on dissolving it in water or to any other solvent, then such isomers are called ionization isomers. For example, molecular formula CONH3 whole 5 Br dot SO4 have possibilities of two different ionization isomers, that are CONH3 whole 5 Br SO4 and CONH3 5 SO4 Br. CONH3 5 Br SO4 when dissolved in water release sulfate ion and gives positive test for sulfate, that is when barium chloride solution is added and dissolved into the solution of CONH3 whole 5 Br SO4, white precipitate of barium sulfate forms. No white precipitate used to form when we add silver nitrate solution in this kind of solution of the compound. The color of this compound is violet. CONH3 whole 5 SO4 Br when dissolved in water, it releases bromide ion and gives negative test for sulfate, but form light yellow colored precipitate which is soluble in ammonium hydroxide when silver nitrate is added into it. This compound is red in color. Linkage isomers. There are ligands which have more than one donating sites. For example, thiocyanate is a ligand which can donate pair of electrons either from sulfur or from nitrogen site. Such ligands are called embedent ligands. Molecules having similar molecular formula but have different structural formula formed due to linkage of different atoms of the same ligand with central metal atom or ion are called linkage isomers. For example, in the molecular formula, COSCN-NH3 whole 5 Cl has two different structures that are formed by the bonding of COSCN or CONCS. For naming such compounds, name of ligands follows the symbol of the donating atom separated by a dash. For example, COSCN-NH3 whole 5 Cl will be named as pentaamine thiocyanato -S cobalt 2nd chloride. Similarly, the compound CONCS NH3 whole 5 Cl will be named as pentaamine thiocyanato -N cobalt 2nd chloride. Coordination isomers. There are compounds that have complex cationic and anionic part. For example, compound CrNH3 whole 6 COCl6 has both cationic, that is CrNH3 whole 6 3 plus, and anionic part, that is CrCl6 3 minus, are complex ion. With the difference in arrangement of ligands, different structures used to form. These different structures are called coordination isomers. For example, two different structures can be generated from the molecular formula CrCONH3 whole 6 Cl3, that are CrNH3 whole 6 COCl6 or CONH3 whole 6 CrCl6. These two compounds are called coordination isomers, coordination position isomers. There is possibility of coordination sphere that can contain more than one central metal ion by the availability of a bridging ligand in it. Different ligands that are part of same molecular formula may associate with different metal ions of the same coordination sphere. Isomers generated by the interchange of ligands between the same metal nuclei are called coordination position isomers. For example, in the molecule which is shown in your screen, amine and chloro group may rearrange themselves to produce different isomers. Now, let's discuss about the second type of isomers called stereoisomers. Compounds having same molecular formula, same sequence of ligating atoms but having different arrangements of or orientation of the ligands in three-dimensional space are called stereoisomers, and the phenomenon is called stereoisomerism. Stereoisomers can be further divided into two parts, that are geometrical isomers and optical isomers. Geometrical isomers. Isomers having same molecular formula and structural formula but different in arrangement of ligands are called geometrical isomers. Since these kind of isomers have same molecular and structural formula, their chemical properties remain almost same, but there becomes a significant difference in the physical properties of the compounds as the net dipole moment of the compound differ, which on result differ the physical interaction of the molecules. For example, PtCl2NH3 is a biologically important compound and have a square planar geometry. In the square planar geometry of the compound, amine group may either be present at 90 degree to each other or may remain 180 degree apart. The arrangements were two similar ligands and adjacent to each other, then the isomers are called cis isomers. While two similar groups are if opposite to each other, then the kind of isomer is called trans isomer. This result with two different geometries, that is cis isomers and trans isomers. You can see net dipole moment in the case of trans isomers is 0, which is not the case cis isomer. Cisplatin is used for the treatment of large number of cancers, while trans doesn't give any kind of activity. Our syllabus specifies the study of isomers of the coordination number 4 and 6. So let's start with the study of geometrical isomers of the coordination number 4. Metal ion having coordination number 4 may frame two different kind of geometries, that are tetrahedral and square planar. Since all the angles in a tetrahedral geometry has identical bond angle, that is 109°28', it is therefore can be concluded that the tetrahedral geometry cannot frame any other arrangement of the ligands. I mean, irrespective of the type of ligands present, that is similar or different, a tetrahedral coordination compound cannot show any geometrical isomers. Another possible geometry associated with the metal of coordination number 4 in a coordination compound is square planar. Here, different cases may be discussed. Let A, B, C and D represent 4 different ligands and M represent central metal ion. Then, following set of square planar geometry can be framed. MABCD. Compound MABCD can form 3 different isomers called A trans to B, A trans to C and A trans to D. You can see the structures here. Ma2BC. This type of compound may form 2 different isomers, A trans to A and A cis to A. Ma2B2. This compound also have 2 different isomers, that is 2 different geometrical isomers, A trans to A and A cis to A. Geometrical isomers of coordination number 6. Let A, B, C, D, E and F represent 4 different ligands and M is the central metal ion. Then the first case is Ma6. In this case, no geometrical isomer is possible because all the ligands are same. Ma5b, no geometrical isomers are possible. Third case is Ma4b2, two different geometrical isomers are possible, B cis to B and B trans to B. Ma3b3, here two different arrangement of ligands can be formed which are certainly not the cis and trans if the 3 ligands are arranged in the octahedral geometry in such a way that the 3 similar ligand is framing a face of the octahedron, then such isomer is called facial or FAC isomers. If the 3 identical ligands is the part of the same plane, then such kind of arrangement is called meridional or MER isomer. I have a question for you. Draw all the possible geometrical isomers for Ma3BCD. There are 6 possible geometrical isomers of Ma3BCD. I hope you can draw the 6 structures here. These structures can be generated by first making 2 geometrical isomers that are meridional and facial with respect to A, and then structures related to those 2 structures can be framed. Now let's learn about the optical isomers. But before this, please revise your learning of stereoisomerism of organic compounds. Now I am revising important points of stereoisomers here. Optical isomers. Isomers having similar molecular formula, structural formula and even same arrangement of atoms or groups but differs in their orientation in its 3-dimensional geometry are called optical isomers. Such compounds are optically active or called chiral. That means when a compound placed in a Nicol prism rotate plane polarized light either right or left from its original position. The compounds that rotate plane polarized light to the right are called dextrorotatory, and the compound that rotate plane polarized light in left direction are called levorotatory compounds. They are also represented by small letters D and L. Non-superimposability is the prime structural features of such isomers. Optical isomers can be divided into 2 parts that are enantiomers and diastereomers. Optical isomers that are non-superimposable to its mirror image are called enantiomers. For example, amine aqua bromo chloro nickel second frame tetrahedral geometry that are non-superimposable with their mirror image. Thus, the compounds and their mirror image are called enantiomers. One can try all the efforts to superimpose them, but this is not possible without breaking the bonds. Diastereomers. Optical isomers that are neither superimposable nor the mirror images are called diastereomers. The structures shown here are neither superimposable nor mirror images. Structurally, the compounds that are dissymmetry will produce optically active compounds. That means compounds that do not contain center of symmetry, plane of symmetry and rotation reflection axis of symmetry are called optically active. In case of coordination compounds, in most of the cases, plane of symmetry provide sufficient information about the optically activity of the compound. So, I am elaborating plane of symmetry a bit, and rest symmetry elements I expect you will learn by yourself. An imaginary plane which when passes through a molecule or object divide that into equal halves, one half of which is the mirror image of the other half. See the structure here. These type of planes are called plane of symmetry. Now let's study about the different possibilities of optical isomers in coordination number 4 and 6. So let's start our study from optical isomers of coordination number 4. Coordination number 4 can result two different geometries, tetrahedral and square planar. In case of a square planar geometry, all atoms are framed inside an imaginary plane and therefore will be optically inactive, irrespective of the fact that how many different ligands are present there. You can see structure. In the tetrahedral arrangement, if two or more ligands will be identical, then an imaginary plane will be automatically passed between them. You can see structure here. In other words, even in tetrahedral geometry, for becoming optically active compound, all the four ligands should be different. Now, let's learn about optical isomers of coordination number 6. Let's start our study from all the monodentates ligand. Case 1, MABCDEF. You all know, if all the participating ligand in octahedral geometries are different, then a total of 15 geometrical isomers can be formed. Any out of 15 such isomers do not contain symmetry elements and are asymmetric, and therefore they all can frame non-superimposable mirror images. Case 2, Ma2BCDE. Octahedral compounds having two identical ligands may frame two types of geometrical isomers, cis and trans isomers. Trans isomer contain a plane of symmetry and therefore will not be optically active, while cis isomers do not contain any such plane and therefore are optically active. Case 3, Ma3BCD. The meridional isomer of Ma3BCD are optically inactive as they contain an imaginary plane of symmetry, while facial isomer do not contain such plane of symmetry and therefore all the three facial geometries, that is of Ma3BCD, are optically active and produces three pairs of enantiomers. Here you can also see diastereomeric pair of such isomers. Now let's move towards optical isomers produced by bidentate ligands. Case 4, MAABCDE. This compound is optically active and for each of such geometrical isomer there would be a pair of enantioisomers. You can see structure here. MAA2BC. There are two possibilities of geometrical isomers of such compounds, that is B and C can be cis to each other or to trans to each other. The trans arrangement is symmetrical with respect to plane of symmetry and therefore is optically inactive, while cis isomer is unsymmetrical with respect to any such imaginary plane and therefore will produce a pair of enantiomer. Case 6, MAA3. The three-dimensional arrangement do not contain any plane of symmetry and therefore can produce a pair of enantiomer that are dextro or levorotatory. Structures are on your screen. Case 7, MAB3. If bidentate ligands is unsymmetrical, then two geometrical isomers can be produced and for each of such compound a pair of enantiomers can be produced. You can see structure here. MAA2B2. The compound may contain two different geometrical isomers, cis with respect to B and trans with respect to B. The trans isomers will be optically inactive as will contain any imaginary plane of symmetry. Cis isomers will produce a pair of enantiomers. Structures are here on the screen. Similarly, you can frame different isomers for a given molecular formula. Two or more compounds having same molecular formula but differ in their structures are called isomers. Isomers of coordination compounds are divided into two broad parts, structural isomers and stereoisomers. Structural isomers are those compounds which have same molecular formula but differ in their net structures. Since physical and chemical properties are directly linked with the structure of the molecule, such compounds have different physical and chemical properties. Hydration isomers, linkage isomers, ionization isomers, coordination isomers, and coordination position isomers are the subparts of structural isomers. On the other hand, stereoisomers are those who have similar molecular structural formula but differ in their three-dimensional orientation. Since metal, ligand and structures of such compounds are identical and therefore the chemical properties of such compounds are similar. Stereoisomers have been divided into two subparts, geometrical isomers and optical isomers. Generally, geometrical isomers differ in polarity and packing of compounds, therefore their physical properties also vary, while optical isomers have same physical and chemical properties but differ in their optical properties, and even physical and chemical interaction of these isomers with an optically active compound changes. From next class onward, we will start bonding theories of coordination compound. Thank you very much for listening me.